Well, we left off with a grid that looked reasonable. We made a boundary layer, which is where all the action in terms of the turbulence and viscosity is going to happen. So in terms of the wing operation, that's essential. We've got a grid size and number of points where the high shear is in the wake of the wing. Seems to be reasonably sized. Now, there's a few things that we can do to evaluate the grid. If we look at the quality, and we can check mesh quality. We can look at mesh metrics, and right now it's displaying none. We can display the first of all the orthogonal character of them, which are the elements that are very skewed. And you can see it generates this plot down at the bottom, and over here it shows the elements that are not skewed. And if we highlight that, then what we're seeing is essentially the non-skewed or good elements, and the ones that are missing are the ones that are relatively skewed. We can select that and we can see those elements that are skewed in to a certain degree. We can select the ones that are more so, and even more importantly, we can look for the real sliver-like ones, and they're the boundary layer elements that are down here at the corner. Now, if we wanted to, we could fix those, and we could modify the mesh to reduce the skewness of them, but for the moment, we'll be content with this. Now, the other thing that we can look at is the aspect ratio, and the elements that have a relatively rectangular aspect ratio are shown here, and those are good because we're doing a control volume analysis. The ones that have a very steep aspect ratio, like so, or find out where that one was. There. So now we've just blown up the y-axis, and we can see that those ones are the elements that are close to the border, which are okay because they're our boundary layer elements, and these, and we have relatively few really skewed elements. So that's not too bad. Now we can look at other aspects of the element quality, and we can see that our element quality that's quite good is pretty high. And if we look at the ones that are especially bad, just check the controls again. The element quality that's good. So our high quality elements are a large number. These, and as we get worse and worse in terms of skewness, they're primarily around the airfoil itself, which is acceptable. There, so now we're seeing all of our elements, and again we've got 23,000 elements, which is a reasonable amount. The maximum we have for the student license is 50,000. So we have a solution volume here that might actually be feasible. One thing that we might want to do is it would be nice to modify the transition between the sphere of influence and the rest of the grid. Right now it's looking pretty radical between those, but we'll give this a try. So I'll just go up and save this file. I'll call it 2D Wing 2. And we're saving. And now we have the mesh. Now, because we made a bunch of changes to it, for one reason or another, ANSYS Workbench wants us to update it. We've got a check mark there. We should be good. Now, if we go to right-click on Setup for Fluent, we should be able to open up Fluent. Now, for Fluent, you'll see it'll pop up. It should show as in 2D. If it doesn't show as dimensions are 2D, then you'll want to go back and make sure that you've loaded your SolidWorks two-dimensional planar file into SpaceClaim and resaved it, because that's been a problem. You'll want to select double precision. That reduces the error per pass. Now, I've tried to use more processors, but for some reason or other, the student license won't allow that. So I'm really stuck to one GPU and one solver. So that should be sufficient. And if you click Start, then Fluent should open up. And here we have our mesh, just as we had done it before. Now you can see that Fluent has already figured out that anything called inlet was an inlet and showing the arrows in, and anything described as an outlet was an outlet. So that's good. Now, the first thing we want to do is if you click check to the grid, you'll see in the console window that it describes some of the statistics of the grid. And if you check that, you can look at those numbers and see that they are what you thought they would be. And if it passes that test, that's good. The scale, you can just double check to see that your dimensions are correct. And this shows that my minimum X is negative 0.3 meters. My maximum is 0.6 meters. So it's a meter long in the calculation volume. And it's a half a meter high. So that looks good. And it's a 2D planar space. And the rest of these are perfectly fine. So that's good. Now, one of the things we want to do is we're solving a whole lot of differential equations here, and ANSYS gives us the ability to choose what models we're going to use. Most of these things are defaulted just as you want. The one thing you might want to change is the viscous model, and if you right click on that, you can see that there's a bunch of different solutions here. We could run a friction-free model or a laminar flow model. For something like this, where we know that the Reynolds number is going to be in the 200,000 range, as it was before, we could pick either of these models, K epsilon or K omega, but we'll use the K epsilon model and a realizable format. It will work in other models as well. And we don't want to define our own turbulent viscosity and turbulent kinetic energy. We'll just leave them as is, and we'll use standard wall functions. And so these are the defaults for those turbulent kinetic energy numbers. Then we look at the materials and what fluids are we going to use. Well, right now it's default to bring in air, and we could look at the Fluent database or the Granta MDS database, which you should have access to, but we don't at the moment. I'm just going to open the Fluent database. I want to find water. There we are, water liquid. And it's got the properties that we think look about right. And we'll copy those there. and you can see that they copied over to this space here. And so we have the choice now of water liquid, not just air. Solid, we don't care about the solid. Now for the cell zone, this is where we define the fluid. And if we right click on the fluid, we can open that up and we should be able to choose water liquid. There. Now the next thing are the boundary conditions. Because ANSYS and Fluent talk to each other, they are fairly familiar with the boundary conditions that the names that we give might be. So because I called my inlet, it's identified the inlet as what would normally be an inlet for flow. And if I right click on the inlet, I'm just going to edit it because I want to specify what the water flow is. And I'm going to specify not magnitude normal to the boundary, but I want magnitude, I could have magnitude and direction, but I'm going to have components. If I chose magnitude and direction, I could give a velocity, magnitude, and an angle, but at the moment I'm just going to pick components. And in this case, my reference frame, my x velocity is going to be 1 meter per second. And my y velocity is going to be 0. And I'll leave my turbulence factors here. Those are fairly normal. And unless we know more about that, which we don't at the moment, we'll just leave those. The internal boundary conditions are inside, and we'll leave those. Those are in the grid itself. We have the outlet boundary condition. Now, because it's an outlet, if we right-click on that to edit, then you'll see that it's already set up as a total pressure, absolute pressure boundary, which is perfectly fine. If we set up the gauge pressure at the outlet at 0, then that's a reasonable default, and everything else upstream, where we've specified velocity upstream and pressure downstream, those two parameters can calculate and work out just fine. Some of these other issues, like preventing reverse flow, we don't want to select any of those. So we'll just apply and close. The last thing is the wall, and it's already identified the wing surface that we named as a wall. And we can edit that. And we could give a roughness if we chose. We specified a no-slip condition, and that's correct. And it's a stationary wall. So all of that looks right. The rest of these parameters, we'll just leave them alone. We can look at the methods now. And setting the spatial discretization is important. The second order upwind solution will be more accurate, but it might also be less stable. In this case, we'll try first the first order upwind, and you'll see that that gives us a bunch of schemes here, and there's a variety of different solution schemes. Without getting into too much of the details, that's more advanced. The simple model is a reasonably robust and reliable one. We can discretize the pressure as a second order, and we're using first order upwind solutions. And so those are all good now. We can look at the controls, right-click on the equations, and you can see that there's flow and turbulence equations. If we right-click on the limits, then this would be our limits of our maximum pressures and kinetic energies and things. So if the solution explodes out of bounds and reaches those limits, it will stop. So that's okay. And we can look at monitors. Now, the monitors are showing us how the solution progresses. And if we want to plot the residual, then that's a really useful monitor. That's the residual of the solution. The other thing we can do, similar to what we did in SolidWorks, are create report plots. If you right-click and you select New, then we can choose a new report plot over here where we want a force report, and we'll choose the drag force. And we'll actually choose a drag coefficient. And it knows that drag coefficient is typically in the x direction. And we'll create that output parameter. And we'll call it, coefficient of drag. And we'll add another one, which will be lift. Coefficient of lift. Oh, and we have to select the zone, which is the wing. And we're going to create an output parameter. Now I have to correct that because I need to select the wing. Drag and lift, and we'll print to the console. So that means as we're solving the problem, we'll be able to see the result. And so now you'll see that we'll get our report of lift and drag as we go along. So with all that, the only other thing we want to do is the initialization. And we can choose to initialize it with any number of things. But since we're starting off with really a plane flow in the horizontal direction, it would make sense to initialize our solution using the output conditions. There. So we've initialized the model. So we're ready to proceed to do a solution. So pitter patter, let's get at her.